Okay, so we're actually on the last lesson of chapter 12, which is really going to pick up from section 12.10, but taking one step further, measuring error. Let's read this theorem up on the top. Let's say f has n plus 1 derivatives throughout an interval containing c. Remember, c is where you are centered. So we're going to say we're centered at c. If x is any number in that interval, and x is not c itself, the error in approximating your function by an nth degree Taylor polynomial, and remember this nth degree Taylor polynomial is written right here, p sub n of x is going to, of course, be an nth degree polynomial. If it was a third degree, of course, we'd see the highest power would be a 3 and so forth. But once again, looking at the coefficient, what's in front of x minus c to the n, the nth derivative of f evaluated at c divided by n factorial. So we're not dealing with an infinite series right now. We're stopping with an nth power. And if we use this polynomial to approximate our function at a given value of x, of course there will be error. And we mentioned this in the previous section. The LaGrange error bound is going to be r sub n of x. It's the n plus 1 derivative, evaluated not at c, but at a number called z. And that's times x minus c to the n plus 1. Notice that we're going one power higher than our polynomial, divided by n plus 1 factorial. Z is a number between c and x, and I want to show you that there are a couple of possibilities. We might be centered here at c. Perhaps the x value that we would like to approximate, let's just say that x is greater than c, that is, your x value would be to the right of c. Z would be some value between c and x. You could see that it would be larger than c here, but it would be less than x. Also, we could come up with this other possibility. What if your x value that you are approximating is actually smaller than c? Well, now you can see that z, of course, is still going to be between x and c. So I guess what I'm trying to point out to you is that your z value is always between c and x, but you can see that your z value might be larger than c, it might be smaller than c, it might be smaller than x, it might be larger than x. It's really all a matter of being between. So let's jump into a little bit more information. When you're approximating functions with Taylor polynomials, it's important to note that there are two main methods for approximating the size of error. We've been doing step 1 all throughout chapter 12. If we have an alternating series, we could use the alternating series estimation theorem, and that's great. But what if we don't have an alternating series? That's the big question. Step number 2 says, in all cases, whether your series is alternating or not, you may use this LaGrange error bound, which we've written up above, and we can use that r sub n of x to tell us what the maximum error is. So let's jump into a specific example, and I think this could really be helpful. I'm hoping that it will be. Let's take a look at f of x is equal to the natural log of x. Find the third degree Taylor polynomial. Find the LaGrange error bound evaluated when we are centered at 1. Use your Taylor polynomial to approximate the natural log of 1.1, but then I've changed the directions a little bit. Use the LaGrange error bound to prove you are accurate to 4 decimal places. So with no further ado, let's just realize that if we're going to go out to the third degree Taylor polynomial, we need 3 derivatives. So very quickly, let's jot this down. We can say f of x pardon me, f of x, of course, is the natural log of x. And very, very quickly, realizing that we are centered at 1, we're going to evaluate all derivatives and this function itself at c equals 1. Natural log of 1, of course, is 0. Continuing on, we can take our derivative. The derivative of natural log of x is 1 over x. And if we were to evaluate that at 1, of course, we would get 1 itself. Now, by the way, to help us on future derivatives, let's realize that the first derivative is essentially x to the negative 1. I'm going to take a second derivative. Using the power rule, we'll drop down our negative 1 times x to the negative 2. And of course, this is really equal to negative 1 all over x squared. Well, if we're evaluating at where we are centered, substitute a 1 into this derivative. Negative 1 over 1 squared, of course, is simply negative 1. Well, let's continue taking another derivative, the third derivative. Again, coming up to negative 1, x to the negative 2. Bring your negative 2 down. Negative 1 times negative 2 is a 2. This is 2x to the negative 3. And by the way, this, of course, would be 2 all over x cubed. But if we were to evaluate this at 1, 2 all over 1 would simply be a 2. Now, here might be a little bit of a surprise. I'm actually going to take a fourth derivative. And all of a sudden, someone might be wondering, well, why are you doing that? You're only asked to find a third-degree Taylor polynomial. Shouldn't we just take a third derivative? It seems so, but if we're talking about error, we're going to go one derivative beyond the degree of our polynomial. We'll have to take a fourth derivative here. 2x to the negative third, bring down the negative 3. 2 times negative 3 is negative 6. That's negative 6, x to the negative fourth. And this will become negative 6 over x to the fourth. I'm going to leave that as such. Very often kids want to substitute a 1 in, but we're actually not going to do that. Let's very quickly take a look at Part A. It says evaluate a third-degree Taylor polynomial. Well, what that's going to be is we're centered at C, so we'll have f of C plus f prime of C times x minus c to the 1 all over 1 factorial plus the second derivative evaluated at c times x minus c to the second power all over 2 factorial. And then, of course, we'll take our third derivative evaluated at c, x minus c to the third all over 3 factorial. Well, if we work this all out, we'll notice that we're finding f of 1. Well, f of 1 was 0, f prime of 1 was a 1 itself, f double prime of 1 was a negative 1, f triple prime of 1 was actually a 2. So this 0 is going to wipe out, and I will have a 1 here, just leaving us with 1 times x minus 1 all over 1 factorial. Then we'll say plus negative 1. Well, you could say minus if you'd like. And this would be x minus 1 to the second all over 2 factorial. Of course, 2 factorial is simply a 2. Then we will say, wrapping this up, this is a 2 times x minus 1 to the third all over 3 factorial. 3 factorial, of course, is a 6. So we're seeing that the third degree polynomial, Taylor polynomial, is x minus 1 minus x minus 1 squared all over 2. 2 all over 6 actually would simplify nicely to just a 3. And there we have it. That is p sub 3 of x, our Taylor polynomial. Well, real quickly we could say, what about the LaGrange error bound? Well, the LaGrange error bound is going to be the fourth derivative evaluated at z, remember. Remember, that's evaluated at z, and we're going to say x minus 1 to the fourth, we're going one step beyond, divided by 4 factorial. And this is for z between where we are evaluating. We're going to evaluate at 1.1. So z is going to be bigger than 1 but less than 1.1. So this is part A. What about part B? Well, part B, we're asked to approximate the natural log of 1.1. So we're going to say p sub 3 of 1.1. And again, what are we going to do? Essentially, we're just going to plug in a 1.1 into our function up above. Well, we could very quickly work this out specifically on the calculator. I think that might be the easiest thing to do. And this should just be a minor calculation. We can see that we're actually going to be accurate to about 0.0953. So that's really what we're seeing for an estimate of the natural log of 1.1. Of course, now we're going to say, well, what about our error? What about this LaGrange error bound? Well, we can say from up above, r sub 3 of 1.1 is going to be the fourth derivative. Now look to the bottom left part of the screen. We'll say that's negative 6 all over z to the fourth times 1.1 minus 1 to the fourth all over 4. But here's where we need to do a little bit of work. We're going to say, and by the way, that's 4 factorial down below, excuse me. We can clean this up a little bit and say this is negative 6, down here is z to the fourth times 4 factorial. And 1.1 minus 1, of course, is just a 0.1, so this is 0.1 to the fourth. You know, if z is between 1 and 1.1, that's really what's going to drive this lesson right now. We have to choose a value for z to maximize the error. And I know that might sound funny, but we're giving a worst case scenario. Imagine that you were trying to explain the worst thing that could happen to someone financially, that it's possible that they could lose $10 or perhaps up to $100. You wouldn't want to tell the person, oh yeah, you would expect to lose $10, and then have them find out that they've really lost $100. When you're giving these error estimates, you want to deal with a worst case scenario. So we'd like to find out what would make our LaGrange error bound the biggest possible. So we're going to look at the 1.1 and the 1. Z is somewhere between those two. We honestly don't know exactly which one it's going to be. We don't know exactly the value of z, but look, z is in a denominator. The smaller your denominator is, the larger your overall value of a fraction is. So what you do, of course, is we're going to let z equal 1. And if we do that, we're going to be able to say that our error is going to be less than negative 6 all over 1. And we could put this in absolute value, of course. And work all of this out. You're going to see, if you work that out on your calculator, your error would work out to this. So what do we really know? We know that we're accurate to 4 decimal place accuracy. Okay, so that's proving that we're accurate to what they asked us to show. Again, choose z to make your error as large as possible. We'll take a look at number 2 in just a minute.